Machine-learned weather emulators operate roughly 100 times faster than traditional physics-based models. This speed enables the generation of massive ensembles of future climate scenarios, calculating centuries of weather in a fraction of the time. When evaluated against historical data, models like the baseline ACE2-SHIELD perform flawlessly. Feed them known sea surface temperatures and historical carbon dioxide levels, and they will accurately recreate the climate record. But historical accuracy is a low bar. To truly stress test an emulator, engineers push it outside the known data by applying a counterfactual, uniformly warming the global sea surface temperatures by exactly 4 Kelvin. These maps show the uniform warming experiment. Despite massive ocean heating, the ML emulator predicts severe, unphysical cooling across land masses. Compare this against the physics-based target model, which obeys thermodynamics by predicting uniform global warming to a +4 Kelvin ocean. A machine learning model that perfectly memorizes historical data is structurally useless for future projections if it violates basic thermodynamic laws the moment it encounters novel conditions. The root cause of this failure comes down to severe feature correlation within the model's training diet. In all observational datasets, rising sea surface temperatures are chronologically linked with rising CO2 concentrations. As one increases, so does the other. The neural network optimized for this specific coupled relationship. Instead of learning the independent thermodynamic physics of carbon dioxide and ocean heat, it learned a statistical shortcut linking the two variables. The +4 Kelvin test forced the model into an empty, out-of-distribution quadrant of its latent space. We asked it to evaluate high sea surface temperatures alongside low historical CO2, a combination it never saw in training, causing its predictive weights to collapse. To build a robust climate emulator, engineers must deliberately break historical correlations. The network has to learn the distinct partial derivatives of sea surface temperature and CO2. Solving this out-of-distribution failure requires abandoning historical accuracy as the primary metric, and instead training the model on completely synthetic, counterfactual Earths. To isolate the exact nature of this entanglement, the AI2 research team ran a specific diagnostic, the AMIP constant CO2 experiment. The parameters of the test are straightforward. Historical sea surface temperatures are allowed to rise normally from 1979 onward, but CO2 is artificially frozen at 1979 levels. This chart shows the failure of the legacy model in this scenario. While the true physics model warms, the ML model predicts a flat trend line, showing almost no atmospheric warming over the 40-year period. This proves a specific mechanical flaw. The network had assigned nearly the entire historical warming trend to the CO2 parameter. Without rising CO2 to trigger its learned shortcut, the model was blind to the immense thermal forcing of the ocean. By contrast, the newly upgraded model, ACE2S SHILD+, successfully tracks the correct near-surface warming, relying on the sea surface temperature forcing alone. High-dimensional ML models will consistently take the mathematically lazy optimization path, unless engineers design datasets that make that correlation impossible. To achieve that decoupling, the team utilized the physics-based SHIELD model to generate a completely new class of ramped SST random CO2 training simulations. The first boundary condition of this synthetic data is a steady, uniform increase in sea surface temperature at exactly 1 Kelvin per year. This chart shows the second decoupled condition. Notice the jagged, chaotic line representing CO2 concentration. It fluctuates wildly, independently of the warming ocean. These injections are severe, drawn randomly every 30 days. You see the forced inverse relationship tracking in stratospheric temperatures below. Sampling this highly randomized matrix successfully populates the previously empty quadrants of the parameter space. By subjecting the neural network to these extreme, non-physical variations, it is forced to separate the fast atmospheric adjustment to carbon dioxide from the slow thermal response to the ocean. We can validate this synthetic training with a definitive test of out-of-distribution climate physics, the slab ocean-coupled abrupt 4 times CO2 experiment. Instantly quadrupling carbon dioxide forces a precise reaction, immediate sharp stratospheric cooling, followed by slow multi-year tropospheric warming delayed by the ocean's thermal inertia. The legacy ML model violates this physics. It instantly skips the transient phase, jumping straight to the final 4 times CO2 thermal equilibrium on day 1. These charts show the newly trained ACE2S Shield Plus model succeeding where the legacy model failed. Panel C shows the precise stratospheric temperature tracking, while Panel A shows the slow, accurate ocean surface temperature equilibration over the full 10 years. Exposure to those abrupt, randomized CO2 spikes during the synthetic training phase provided the network with the exact e-folding timescale required to emulate stratospheric adjustment. An abrupt quadrupling of CO2 forces a massive reorganization of the planetary hydrological cycle and top-of-atmosphere radiative fluxes. These maps show the response of latent heat flux over the oceans. The upgraded model accurately predicts the expected reduction specifically over the subtropics, avoiding the massive error patterns of a legacy model. Highlighting the spatial patterns in these panels, we see the model captures the decrease in upward shortwave radiation at the top of the atmosphere, particularly over marine stratocumulus regions off the western coasts. The neural network manages to replicate this complex cloud albedo response despite having no explicit hard-coded parameterizations for clouds. When a network learns the true independent boundaries of a physical system, it can accurately infer complex subgrid physical relationships entirely from the macroscopic state variables. This new training methodology optimizes the model's computational efficiency and total training footprint. This chart illustrates the efficiency gain. The upgraded model achieves multi-domain flexibility while training on 25% fewer total data samples than its specialized legacy predecessors. The 90-year training diet requires a precise mixture, carefully balancing standard AMIP data, equilibrium slab ocean data, and those crucial random CO2 datasets. The engineers added a final architectural touch for pure interpretability, a global energy conservation corrector that mathematically ensures the total atmospheric energy budget remains closed. In high-dimensional ML emulation, the orthogonality and diversity of the data matrix are vastly more critical to generalizability than the sheer volume of observational samples. As machine learning climate modeling moves forward, we have to explore highly complex, mixed emission pathways. Next-generation models will need to decouple variables far beyond CO2. They must isolate the independent forcings of methane, heterogeneous aerosols, and dynamic land ice changes. The industrial era has only happened once. Because of that, all our most critical planetary variables are hopelessly coupled together in the observational record. Purely data-driven models will collapse when projecting extreme edge cases, unless engineers artificially sever those historical relationships. To successfully teach a neural network the true physics of our Earth, we have no choice but to train it on worlds that have never actually existed.